Welcome everyone. This session is on semantics. If you're looking at the printed copy of the handbook, it corresponds to session 7A from Tuesday. The first stop will be by Varada.
Thank you. Thanks for coming. My name is Varada Kolhatkar, and I'm presenting our paper, Resolving Shell Nouns. This is joint work with my advisor, Graeme Hirst. Okay, so what are shell nouns? Shell nouns are abstract nouns such as fact, issue, decision, and problem. These nouns themselves are unspecific and can only be interpreted together with their shell content. That is, the propositional content they encapsulate in a given context. Here is an example. The municipal council will have to decide whether to balance the budget by raising revenue or cutting spending. The council will have to come to a resolution by the end of the month. This issue is dividing communities across the country. In this example, the shell noun phrase is this issue, and its shell content is this weather clause marked in blue. Now, if you want a computer system to understand a discourse like this, then it is important to identify links between shell noun phrases and their shell content. We call this process shell noun resolution, and this paper is about this problem. Now, before I tell you about our method, let's look at the context of the problem. How many such nouns are there in English? The linguist Hans-Jörg Schmidt has extensively studied shell nouns. He provides a list of 670 nouns that can be used as shell nouns. Here are a few examples: fact, issue, problem, principle, decision, thing, concept, reason, notion, phenomenon, and so on. Now, why do we care about this problem? First of all, shell nouns occur frequently in all kinds of texts. So Schmidt observed that the shell nouns fact, idea, and problem are among 100 most frequently occurring nouns in the BNC. Then shell nouns occur frequently, particularly in argumentative texts such as political debates. For instance, politicians are proficient in characterizing their ideas as facts and advantages and their opponents' ideas as issues and problems. Shell nouns play an important role in organizing a discourse. They have this capability of characterizing and labeling complex chunks of text in complex chunks of information in text, and in that way, they facilitate efficiency by avoiding repetition of long spans of text. So resolving shell nouns can be useful in a number of computational linguistics applications such as text summarization, non-factoid question answering, and ESL learning. Okay, so now if we want to resolve shell nouns, we need to consider different constructions of shell nouns. Now, shell nouns can occur anaphorically, where the shell content precedes the shell noun phrase, or they can occur cataphorically, where the shell content follows the shell noun phrase. Now, we refer to anaphoric constructions of shell nouns as ASNs and cataphoric constructions as CSNs. And these are the most frequently occurring constructions in text. That said, there are other usages of shell nouns as shown in the last two examples. In the third example, a bad idea does not harm until someone acts upon it. The shell content of a bad idea is indefinite, and a computational system cannot do much with such examples. Then the last example demonstrates a non-shell noun usage. In this example, the noun issue is used with its publication sense, and it's not a shell noun usage. And the focus of this paper is resolving cataphoric shell nouns, that is CSNs. Now, what is the state of the art of resolving shell nouns in computational linguistics? Now, shell nouns have received fair amount of attention in linguistics, but they have been largely ignored in computational linguistics. If you consider current reference resolution systems, most of them focus on expressions that refer to specific kind of entities, which are generally noun phrases. So over the past few years, we have developed a number of approaches to resolve shell nouns. So our long-term goal is to develop an end-to-end shell noun resolution system. And accordingly, we have developed bits and pieces as shown in this jigsaw puzzle. So first, we developed an approach to resolve anaphoric and cataphoric occurrences of 6 prototypical shell nouns. For cataphoric occurrences, that is CSNs, we developed a rule-based system based on lexicosyntactic patterns suggested by Schmidt. And then we drew on the observation that cataphoric occurrences are easier to resolve than anaphoric occurrences. And we use the training data extract from cataphoric shell noun, cataphoric shell content to resolve anaphoric shell content. Then we developed an approach to reliably annotate ASNs for evaluation. And this work is the missing piece in this jigsaw puzzle. In particular, in this work, we generalize CSN resolution, that is cataphoric shell noun resolution, which in turn generalizes anaphoric shell noun resolution, and which kind of completes this end-to-end shell noun resolution system. So our goal is to resolve cataphoric shell noun occurrences. Now, how do we know that a given example follows cataphoric shell noun occurrence? The linguist Schmidt provides some lexicosyntactic patterns to identify, which are suggestive of cataphoric shell noun usage. Here are the patterns with their examples. Now, the patterns are mainly of 2 forms. The first form is NB clause, where the shell noun phrase occurs as the subject of the subject-verb clause construction with the linking verb be, and the shell content is embedded as a WH clause, that clause, or to infinitive. Then the other form is this N clause form. And in this case, the shell content is embedded as a complement clause, complement WH clause, that clause, or to infinitive. Now, if we look at these patterns and these examples, it seems like it's fairly easy to extract shell content of the given shell noun phrase. But unfortunately, this problem is not that simple, and a number of challenges are associated with this task. The first challenge is that each shell noun has its idiosyncrasies. And so different shell nouns have different syntactic and semantic expectations, and they take different number of semantic arguments, one argument representing the shell content and others representing circumstantial information about the shell noun. For instance, the shell noun fact expects one propositional argument and the shell content is given in that argument, whereas the shell noun reason expects 2 semantic arguments, cause and effect. And the shell content is given in the cause argument and not in the effect argument. For instance, in this second example, one reason that 60% of New York City public school children read below grade level is that many elementary schools don't have libraries. Now in this example, the first that clause is the effect and the second that clause is the cause. And the shell content is given in the cause and not in the effect. The reason here is given in this cause clause. Now at the conceptual level, once we know which semantic argument represents the shell content, it seems straightforward to identify the shell content. But at the implementation level, it's not that straightforward because of the parsing errors. So these kinds of shell noun examples, they generally follow complex syntactic constructions. They have embedded clauses and coordinations and so on. So for example, here I have 2 examples. The first one says, the fact that she pointed out is that nobody on the panel was an expert. Now in this case, the postnominal that clause, it's a relative clause. It's not the shell content of fact. And in the second example, the fact that nobody on the panel was an expert is the source of severe criticism. In this case, the postnominal that clause is the complement clause. It's not a relative clause, and it is the shell content of the fact. But the parser is unable to distinguish between these relative clauses and complement clauses. So in general, resolving CSNs in many crucial respects a semantic phenomenon. For example, if we want to resolve one reason in the example we saw before, we need to identify three things. First, this particular shell noun reason expects two semantic arguments, cause and effect. Second, that the shell content is given in the cause and not in the effect. And third, identifying the particular syntactic constituent that represents the cause in the given context. Okay, so now where can we find this kind of semantic knowledge? So we exploit Schmidt's semantic families for this problem. Schmidt groups together all 670 nouns into about 79 semantic families. Here is an example family, an idea family. Now each family has 4 attributes. The most important ones for us are these last 2 attributes, nouns attribute and patron attribute. The nouns attribute gives the list of nouns subsumed in that family. Now all these nouns share similar semantic arguments. So yeah, they tend to take similar kinds of semantic arguments. A noun can occur in more than one families. And then the second attribute is patrons attribute, which tells which clauses are appropriate for shell content. So they act as cues for identifying shell content. Now, how do we use the knowledge encoded in these semantic families to resolve shell nouns? Now, so the problem is, so Schmidt has these families, and then each family, what we do is, given a shell noun, we extract we consider all semantic families in which that particular noun occurs. Then we list this cues given in those families, and if those cues are satisfied, then we extract it as the shell content. Otherwise, we don't extract it as the shell content. Okay, so let's consider this example. There is now some question whether the country was ever really in a recession. Now, first we parse this sentence using Stanford parser. Then we look at the families in which the shell noun question occurs. Now, Schmidt's cues say that if the postnominal clause is a WH clause, extract it as the shell content. So, in this case, the postnominal clause is a WH clause, and it's a complement WH clause, so we extract it as the shell content. Now let's look at this other example. The question that Japanese movie people most frequently ask the American visitor is, why blah blah blah. So in this case, we want to resolve question, but Schmidt's cues say that if the postnominal clause is not a WH clause, don't extract it as the shell content. So in this case, since the postnominal clause is a that clause, we don't extract it as the shell content. Okay, so that now that we have this method that uses Schmidt's semantic constraints, Schmidt semantic cues, if we want to evaluate that, we need reliably annotated data. Now, it's kind of impractical to extract annotated data for all 670 nouns. So what we did was we selected 6 semantic families with 3 goals in mind. The first goal was we wanted a variety of shell nouns. Then we wanted to see how well shell nouns from a particular family, so whether the algorithm works on the shell nouns from a particular family, and how well the algorithm works from nouns from different families. So we selected these 6 families and then selected these 12 shell nouns. Then we created this cataphoric shell noun corpus. For this corpus, we considered the New York Times corpus as our base corpus. Then we extracted 100 instances per each of our 12 selected shell nouns. And then for our annotation, we used crowdsourcing. So our interface looks somewhat like this. So what we do is we highlight the shell noun phrase, and then we systematically extract plausible candidates for the shell content for that particular shell noun. And here are the candidates for this particular example. And the annotator's task is to select the candidate that represents the shell content of the given shell noun phrase. So in this case, a reliable annotator will select this option B, that many elementary schools don't have libraries. So we asked for 5 annotators to annotate our instances, at least 5 annotators. And here are our annotation results. Now the first bar shows the percentage of instances on which at least 5 annotators agreed on a single answer. So that is, all annotators agreed on a single answer. Then the second bar shows percentage of instances on which at least 4 annotators agreed. Similarly, third bar shows percentage of instances on which at least 3 annotators agreed, and so on. So as we can see here, for about 96% of the instances, at least 3 annotators agreed on a single answer, which is kind of an indicator of reliably annotated data. Okay, so as a baseline, we extract the complement clause depending upon the pattern the example follows. So for example, our baseline in this first example, the fact that nobody on the panel was an expert is the source of severe criticism. Our baseline system will extract this post-nominal clause as the shell content, which is correct in this case. Now let's look at this second example. Women had good reason to expect a steady and inevitable progression toward gender parity in politics. Now in this example, the baseline system will extract this post-nominal infinitive clause as the shell content, which is not right in this case. Okay, so now here are our results. What we did was we considered the crowd annotated data as the goal data, and so here in this graph, on the x-axis we have our 12 shell nouns, on the y-axis we have accuracy, then blue bars show our baseline results, and green bars show results using Schmidt's cues. Now as we can see here, for most of the shell nouns, the green bars are bigger than the blue bars, except for 4 of them, and I'll talk about the 4 of them later. Which kind of suggests that semantic knowledge from Schmidt's families is helpful in resolving CSNs. Then our second result is that Schmidt's cues especially help in resolving nouns with strict semantic expectations. That is, so by strict semantic expectation, what I mean is, so the nouns fact and reason, for them, they tend to occur with these specific kinds of clauses. So if you look at families in which fact occurs, it occurs in 2 families, think family and certainty family. And the allowed clauses, according to Schmidt, are that clauses for fact, and for reason it's just that clauses and because clauses. So in that case, they have strict semantic expectation, and the results are markedly better than other shell nouns. And for the shell nouns, which are more flexible, that is, which can take a number of syntactic or semantic arguments, so the Schmidt's cues were deleterious for such nouns. So which kind of suggests that Schmidt's cues are defeasible because they missed a number of cases in our data, but it is possible to improve these cues using crowdsourcing annotation and extracting patterns from a variety of corpora. So to conclude, we proposed a general method to resolve shell nouns following cataphoric constructions. Our research suggests that semantic knowledge from Schmidt's families is helpful in resolving CSNs, that is cataphoric shell noun occurrences. And Schmidt's cues are defeasible. They missed a number of cases in our corpus, but it is possible to improve on these cues using crowdsourcing annotation and by exploiting lexicosyntactic patterns from a variety of corpora. Then a number of future directions are planned for this work. An interesting one is clustering. So shell nouns are very much similar to verbs in the sense that they take these different numbers of semantic arguments. And so clustering shell nouns with similar semantic expectation, shell noun usages with similar semantic expectation, similar to verb clustering is one future direction. And then other future direction is developing a robust machine learning approach along with this linguistic knowledge from Schmidt's semantic frames. And thank you.
Question?
You said you were focusing on cataphoric constructions because they were easier. Is that just because the content tends to be closer to the shell noun in cataphoric constructions?
So they are easier. I mean, before when I started this work, I thought cataphoric constructions are easier, but then they are easier than anaphoric constructions in the sense that the content is as you said, the content is closer. In anaphoric constructions, the shell content can be anywhere in the given paragraph or page, whatever. But later when I started working on it, I realized that it's not as easy as I thought because of all these challenges I told you before.
You mentioned that parsers get these constructions wrong, and you showed an example then with the wrong parse with the complement clause. What are your plans for dealing with that part in particular?
I mean, I don't really have a plan. So I guess one thing, because first thing I want to do is I want to tease apart so in my baseline, what are the errors that are just because of the parsing errors? Because in many cases, because parser is not able to identify, distinguish between relative clauses and complement clauses, most of the errors are because of that. So if I'm able to tease apart those errors, then I will be able to say clearly. So right now, Schmidt's cues are kind of correcting those parser errors and telling me that, okay, if this is the postnominal clause is of this form, then extract it as the shell content. But if I'm able to tease apart those errors, then maybe I will have a clearer picture of what is happening.
Semantic clustering of verbs. Can you elaborate how you think this semantic clustering can actually help in resolving the CSNs?
Yes, so actually, okay, so the future direction, one of the future, I haven't worked much on this direction, but the thing is, right now I have semantic frames given by Schmidt. And so he used certain corpus and then some features. So maybe he did some corpus analysis and then combined all these nouns that he thought have similar semantic properties. But then if I have some robust clusters using some machine learning approach, then that can help me to verify, then I will get a better idea how good is Schmidt's classification for resolution purposes.